So I guess we can start. I'm happy to introduce Professor Myungho Kim at Kyung University, which is the best university in Korea. He's going to talk about monoidal categorification of that algebra, bosonic extension associated to a positive braid B.
Thank you for the introduction. So today I want to talk about the monoidal categorification of the bosonic extension associated to a positive braid B. So I think I need to explain all the term in my title in an hour. So I need to be hurry up. This is a joint work with Masaki Kashiwara at Kyoto University and Se-jin Oh at Sungkyunkwan University and Euiyong Park at University of Seoul. Yeah. So title. So here's my plan of today. So first, I needed to define the bosonic extension, the algebra in the title. So A hat B. So here B denotes the positive braid. So this is an algebra, the associative algebra, given by whenever we have a positive braid B, then we will have some algebra A hat B. And the second is the reason we are interested in this algebra is because we are interested in the finite-dimensional representations over the quantum affine algebra. UQ prime G hat. So this is my notation for the quantum affine algebra. Three is, so I need to explain what does it mean, the monoidal categorification. So for this, so I introduce the cross algebra very briefly. And at the end, I'm talking about the monoidal categorification of A hat B. So briefly speaking, so today I want to focus to introduce the first two things, and I'll I'll present our result on number 4 briefly. So here the meaning of the monoidal categorification is more precisely, we have a monoidal categorification of the cross algebra structure of this algebra. So it's more precisely of the cross algebra structure of this algebra. So for this, I need to introduce what does it mean, the cross algebra here. Yeah. Okay, so the first thing is the bosonic extension. So today I'll fix. I only think about the simple real algebra over C over AD type. So let's consider that G is a simple real algebra of complex numbers of AD type, and the C is the corresponding Cartan matrix. This is a Cartan matrix. And then, so first, let me define the algebra A hat. So the input data is our simple real algebra. So we write A hat G in this way. So this is the algebra over rational function field in T to the square root of T. So T is a formal variable, so we are in generic cases. It's generated by So we have infinitely many generators. So here I is the index set of simple root of our Lie algebra, and the P is P runs over the whole integers. So we have infinitely many generators. With the relations, so for indices I and j in I and the integer m and p, so we have the following relations. The first one is so-called the quantum set relation. So 1 minus Cij. So Cij is the entry in the Cartan matrix. It's minus 1 times 1 minus Cij. Okay. We consider the quantum integer, and the Fip to the power is 1 minus Cij minus k, and the Fjp, and the Fipk to the k is equal to 0. Yeah. So for if I is not equal to j. So the first relation is the so-called the quantum set relations. So you can easily see that if you are familiar with the Greenfeld-Jimbo type quantum groups, then this is nothing but the usual quantum set relations. So please look at that. We fix the second parameter p all the same. So only p appears in this relation, right? So if we consider the subalgebra of this algebra generated by Fip and the p is fixed, then those generators is just generate the half of quantum groups. Thank you. I think, yeah, you're right. It's minus 1 to the k. I guess so. Yeah. Thank you. Yeah. And so we should understand this algebra as the infinite tensor product of the half of quantum groups. So half of quantum groups generated by Fi's together with the first relations only. And we have infinitely many copies of half of quantum groups. And we need to glue the adjacent two copies. So that's the second relation. So Fim and Fip, if we multiply those two generators, Fip and Fjp, then it's t to the minus 1 times p minus n plus 1 of Cij times Fjp and Fim. So there is some t commutation relations together with some error terms. So the error term is given by this formula, delta of ij times delta p to the m p and n plus 1 and 1 minus t square. Here, if p is larger than or equal to m. So as I told you, the first one is so-called the Q-set relation, quantum set relation. And the second relation is called the quantum boson relation, the Q boson relations. Yeah, so we change the order of the generators, then you will get some error terms, which depend on the I and J and the P and M. Yeah, that's all. So this is the definition of our algebra A hat. So as I told you, so if we consider the algebra, say A hat P, so this is a subalgebra generated by the generator Fip, P is fixed, then this is a subalgebra, and it is isomorphic to the half of quantum groups. Minus. Because half of quantum groups generated by Fi together with the Q-set relation only. And the second, yeah, we can prove that by this, this whole algebra is isomorphic to the infinite tensor product of copies of half of quantum groups as a vector space. So the name bosonic extension comes from the second property. So we can think about that. We are interested in the half of a quantum group, and we take the infinite tensor product of them, and we extend the algebra structure of half of quantum groups on the infinite tensor product. And the number 3 is it's Hernandez and Leclerc studied, introduced actually this one. In order to study the finite dimensional representations, the Grothendieck ring of some subcategory, but yeah, let me just consider this way. So UQ prime G is the quantum affine algebra. The quantum affine algebra module category. So Hernandez Leclerc introduced this new algebra structure to study the Grothendieck ring of the finite dimensional modules of a quantum affine algebra. So prime is yeah. So this is just my notation for quantum affine algebra. So there are several different algebras, and the people all called it as a quantum affine algebras. So my one is UQ prime G, and you can think about that this is a quantum affine algebra, which is a central extension of the loop algebra by some canonical central element only. We have the no derivation generator here. Yeah, let me skip the definition. Yes.
So your A hat
Yes.
is not the U prime of G hat.
No.
No.
No. So my A hat is yeah. So actually, what happens is there is some subcategory of the UQ prime G finite dimensional module of quantum affine algebra. So that's the so-called Hernandez-Leclerc category. It's a monoidal abelian subcategory of this category. Then the correspondence is following. So if you consider the Grothendieck ring of this Hernandez-Leclerc category, and you consider A hat here, so please note that I start with the finite dimensional real algebra here, and this is a module category of a quantum affine algebra. And there is a homomorphism from here to here. And actually, if you use a specialized T equal 1, then they are isomorphic. So the bosonic extension is the T deformation of the Grothendieck ring of the finite dimensional module category of quantum affine algebras.
In item 2, I feel
I'm sorry. Thank you. Yeah, A hat. Yeah. So this is the whole algebra A hat, and in the title you can see that the bosonic extension associated with the positive braid B, the A hat B, and the A hat B is the subalgebra of my A hat. So let me to define this one, we need the following. So braid group X on this algebra. So let me give you the definitions of braid group action. So generator, so I'll define the operator automorphism Ti on this algebra. So it sends the generator Fjm to the Fi n plus 1 if I is equal to J. And it doesn't change, it changes nothing if I is not equal to J, and they are not adjacent. I'm sorry, is equal to 0. They are not adjacent in the thinking diagram. So if they are far from in the thinking diagram, then Ti doesn't change Fjm. And the last one is the most complicated one. So 1 over Fjm, Fim minus 1 over 2. This way, yeah. So if I is not equal to J, but they are adjacent in the thinking diagram, then we have the following formula for Ti. So actually this Ti is the same thing. Yesterday, Ivan's talk, he's talking about the Lussdick braid symmetry on the quantum groups. So Lussdick braid symmetry is the automorphism of the whole quantum groups, actually. So if you restrict the Lussdick symmetry on the half of quantum groups, then you will get the same formula. And by this, the first formula, we can extend it to the whole, the infinite tensor product of half of quantum groups. So we have an automorphism on A hat. So actually, this is not only automorphism, it satisfies the braid relations. So that what I mean is there is a braid group action. This is a braid group associated with our finite dimensional real algebra G. So here, so let me denote by sigma I, the generator of the braid group. Then the sigma I is mapped to Ti. And and the Ti satisfies the braid relation. That's the point. So now, because of this braid relation, braid group action, I mean, so having this braid group action is already non-trivial at all. It's not easy to prove this one by hand. I mean, it's complicated enough to prove this. So you need to work. It's a very good question. So, yeah, it's faithful. Yes, you're right. When G is finite dimensional over AD types, then we can show that it is faithful. Faithful action. Yes. But beyond the finite types, we don't know that. Yeah, let me just give you a remark. So today I start with the finite dimensional real algebra G. But until here, so we can do the same thing for arbitrary symmetric algebra, algebra 2. So nothing changes. All are the same. But this action is faithful when the G is finite type cases, and we don't know beyond that. Yeah, so now let's take a positive braid element B. So this is the monoidal positive braid. Then we can define the following. So A hat B is defined as the intersection of the subalgebras of this form. So where so non-negative is the subalgebra generated by FIP. It's P I is I, and the P is non-negative. And respectively, you can think about a negative as the subalgebra generated by FIP. The P is negative. So I'll define the A at B as the intersection of those two subalgebra. So here is the reason. So if you look at this formula, then the FJM is still remain in the mth part of the algebra, or it moved one to the right, right? So if you apply the positive braid several times, then your generator moves to the right. And you intersect with the non-negative part with this one, then you will get some reasonable size of subalgebra. That's what we want to do here. Yeah. And so I can explain more about the meaning of a reasonable size here, because we have a nice basis of this algebra. So let me call it the PBW basis. So let's fix an expression of positive braid B. So we fix the sequence I1 to IR. Then, so the element Pi, the case element Pi is defined by this Ti1, Ti2, Tik minus 1 of Fik of Jefferson. So R. So for each K from 1 to R, we apply the braid symmetry several times. Yeah. This one? This one?
I think the boldface I for sequence I.
This one. Yeah, I'm sorry. Yeah, you're right. So it's a boldface of I. I1 to IR. Thank you. Thank you. Yeah. Yes. So it depends on the choice of I. Yeah, so if we fix this I, then we can define the R many element in our algebra. And by definition, it belongs to this subalgebra. And actually, what happens is and then we have the following. So we take the product, the ordered product of these generators into the I of A1, where the exponents are non-negative. It gives a basis, actually the basis over the Laurent polynomial ring, or basis of A hat P. So yeah, so because we call this element as the PBW generators, and the ordered product of PBW generators gives the basis. That's the PBW basis. So from this one, we can easily observe the following. So if we consider A hat B and the T, if you specialize the T equal 1. So to do this, you need to take the lattice generated by this basis, and you evaluate the T by 1. Then it is a polynomial ring with R variables. Yeah, so okay, so we have a nice algebra and a nice basis. And I gave us a little hint here that we are interested in this algebra because it does give us also a deformation of the Grothendieck ring of finite dimensional modulus of quantum affine algebras. But this one is the Grothendieck ring of the whole category in some sense. But here we have a subalgebra, right? So the next question is that what is the corresponding subcategory of this subalgebra, which is comparable with this isomorphism? So let me move to the next topic, the finite dimensional representations over the quantum affine algebra. Yeah, so today, I'll fix G hat as the following. Let me see. Yeah, I think, yeah, and set the K. So my affine algebra, real algebra is the loop algebra together, the central extension of the loop algebra. And we consider the quantum deformation of this affine algebra. That's my UQ prime G. So as I told you, some people consider the different affine algebra and that they consider Q deformation. So this is, the notation for this one. So I do not give the definition of this one. You can just consider it a Q deformation of this one. Then the category of finite dimensional modules over quantum affine algebra Q prime G hat is, this is a category of finite dimensional over UQ prime G. I don't know. So I think so. I'm sorry. So usual the affine Casimudi algebra is usually defined together one more central section by the degree operators. And if you take the derived subalgebra, then I think that it gives this one. So in that sense, people put prime here. I think that's my understanding. I'm sorry. So it's not. I was hesitated this. So X. No. So because this is so this is an abelian. And let me denote my base field as the algebraic closure over the ring of relational functions here. So I just want Q to be generic, and I want to have the algebraic closed field. So this is not very significant condition here, and this is an abelian K-linear rigid monoidal category. Because it's a Hopf algebra, so we have a K-linear monoidal and rigid category. So I think it's confusing. So here T is the deformation parameter for the bosonic extension, and the Q is the deformation parameter for the quantum affine algebras. So they are different. Yes, in my note, I wrote T by Q. It's totally wrong. So it should be difference. And this category is interesting because it's difficult to understand, I think. And even though there are many things unknown, for example, the simples are classified over simples with Barichari and Presley. So any simple is over this form. So you consider. So let me explain the notation a little bit later. B 1 tensor product and phi of I to the U. U. I'm sorry. And B over U So this is some tensor product of simple modules. I'll explain it later. So yeah, I can explain that. So this V phi sub I is called the fundamental representations. So they are really fundamental representations in this category because every simple can be obtained as a tensor product of fundamental representations together with some spectral parameter shift. And you can take the simple head of this tensor product, and every simple is of this form. So where, so V by I, so I is the index set of the finite dimensional simple algebra here. G is the fundamental representations. Of our quantum affine algebra. And there is some automorphism on this quantum affine algebra, which gives you the spectral parameter shift. So this is a twisting, the action is twisted by some automorphism. And the automorphism is defined depend on the choice of parameter. So we call this a spectral parameter shift. So there are finitely many fundamental representations, and you can consider all the spectral parameter shift. So there are infinitely many fundamental representations. And if you take some ordered tensor product, then it has a simple head, and those simple head exhaust all the simple objects in this category. Yeah, in type A cases, this spectrum, so I think you are talking about the UQG is a subalgebra UQ prime G hat. And along this embedding, you can consider the evaluation modules, right? But the evaluation module works only type A cases, I think. Yeah. And some parameter shift can be understood as some evaluation modules, but it depends on the parameters. Yeah, okay, let me give you an example. Yeah. I think I can. Oh. Geez. Let's consider SL4 case. So this is type A3. So the column denotes the index for the fundamental representations. And I'm sorry, the rows are fundamental representations, and the columns are the parameter shift. This way. Then let's consider the first fundamental without shift here. And I'll move to the first fundamental shifted by Q square. And let's consider the first fundamental shifted by Q to the fourth. And the first fundamental Q to the shifted by Q to the sixth here. And for the second fundamental, I'll choose the parameter shift is Q to the odd powers. By second is Q to the 1. And this is Q to the cube. Its power here. And the last one, the third fundamentals, I'll take the even power of cube. Three. No, this is 3. Yeah. q to the false. And this is last one is 3 q to the 6. So as I told you, so here the spectral parameter shift and A is this is a spectral parameter shift of module n. So here there exists a automorphism tau A, UQ prime G, and A is for any scalar, non-zero scalar, you can consider this automorphism actually. But here I want to just consider the subcategory generated by those fundamental representations only. What I mean is let's consider the category C of Z. This is the so-called Erlander-Lucley category. So this is a subcategory of UQ prime G mode, which is generated by the first fundamentals shifted by even integers, and the second fundamentals shifted by odd integers, and the third fundamental shifted by even integers. So let's consider the monoidal abelian subcategory generated by those still infinitely many fundamental representations, but we consider the discrete subset of all the spectral parameter shift. The reason is that the Erlander-Lucley observed that it's enough to consider this category to study the UQ prime G mode, because all the essential informations of the category is contained in this smaller category. Yeah, I think okay. So now I want to relate, I want to give some relation like this for boson extension and the subcategories. I'll explain this one. So let's consider a family of simple objects in the Erlander-Lucley category is such that a family of simples such that so we consider the condition like this Li. So let's draw a graph. So for those simple objects are the vertices, and we add edges. So there is edge from between Li and Lj if Cij is -1. Let me see what I'm. No. I'm sorry. So Li tensor Lj is simple. No, simple. So let's consider this graph. So for example, if we take these three fundamental representations, so this is my L1, L2, L3, then you can consider the tensor product between of them. And what happens is that those two do not, the tensor product of those two is not simple. Yes. Yeah. So finite-dimensional simple algebra. So here So here I want to, in this example, I need to take three simple objects in this category, which satisfy some conditions. So for example, you can take those three. Then those two, that gives a non-trivial, non-simple tensor product. And those two gives us a simple tensor product. So in this way, so we obtain the thinking diagram of A3. Or thinking, yeah, the thinking diagram. Of type affine algebra G. Different row or different columns, and or even you do not need to consider the fundamental representations. You can consider the general simple modules satisfy the conditions. And this is, yeah. And we may consider the tensor product with the dual of Li itself, then is simple for k is not equal to 1. And the third condition is that Li tensor, the dual of Lj, is simple for k is not equal to 0. So in these cases, so let me, yeah, this one. So yeah, I'll explain the meaning of this triangle later. So this module is the right dual of the first fundamental. So I'm sorry, so D denotes the right dual of module M. And you can consider the power of D, and the negative power means the left duals. K times right duals. So this is, so I think the D square, this is a D square, the 8. For example, 1 q to the 8. So right dual of this one is this one. No, I'm sorry. Yeah. 10th power. The first right dual is this one, and if you take one more right dual, then you have this one, and so on. If you take left dual, then it goes to the left. And one more condition here is that every simple first can be obtained in this category is of the form the head of some order, the tensor product, but the order is decreasing order, M1, tensor of the 0, M, 0, of this form where each M K's belong to the category I denoted by C of D, which is the category generated by simple object we choose. So I'm sorry, so this is a simple head. So maximal the largest semi-simple quotient, which is tensor. And in this case, it is simple. So here so if we choose those three, and we consider the monoidal subcategory contain those three, and which is closed under the extension and subquotient, then you will get the other three fundamentals to that. So we conclude that the category CD here is actually generated by those simple those 6 fundamentals. Yeah, this is the triangle. Yeah. And the last condition is something like that. So you can produce all the simples in the analytical category by just taking the simple modules in this triangle and it's shifted by duals, right? So, and you take a tensor product and head, then you will get all the simples. But in some sense, so this choice generates all the simples in this category. No. No, thank you. Yeah, that's very nice question. So, so what happens is the following. So if we have two simple module M and N, for example, if they are simple, and let me consider the spectral parameter shift here, then they are isomorphic except for finite many x. But what I mean is that generically they are isomorphic, but it's for special choice x they are not isomorphic. So it's not braided, but so we can say that it's generically braided, but it's not braided exactly. Yes, yeah. So it's important for given pair M and N, finding the spectral parameter X such that they do not commute. It's important problems. And yeah, this is what I did here, actually. Yeah? If they are simple, then we do not draw edge, but if they are not simple, then we do not draw edge. And I explained that we have that thinking diagram, right? But you need to calculate these conditions for those modules. Yeah. Yes, that's important. Yeah. So, so the fundamental representation cases, those x are known completely. Yeah. So there are the calculations. Or in this case, AD type. So there is a very beautiful formula for producing x. So let me give a theorem. So for any D, so we call those, yeah, this D is a very special family of simple modules, right? And we call it the complete duality datum. It's just a name of this family with this property. So for any complete duality D, so I and I, so there exists a unique surjective algebra homomorphism let me denote by sub D, which comes from the integral form of the bosonic extension to the Grothendieck ring of another category, which send the generator FIP to the right dual of piece right dual of Li. And so T goes to 1. So here, this is F1, 0, because there are no T equals 0 cases. So this is F2, 0, F3, 0, and this is F1, 1. The shifted by F1, 0 shifted by 1. This one. So you can, yeah, so you can see that the generators in this category. image of generators in this category. And such that, when t equal, it gives isomorphism. That one, A hat t equal 1 is isomorphic to the Grothendieck ring. This is the statement for number 3 here. And and moreover, so phi d gives a bijection. So between I do not give the definition of the global basis, but there is a very nice basis for the bosonic extension. We call it global basis with the set of simples in the category CG. So we have a ring homomorphism. So as I told you, so this is a polynomial ring. And it is a polynomial ring because it is generated by the fundamental operations. So in this example, the both are polynomial ring with 6 variables. So they are isomorphic, of course, right? But this isomorphism is very nice. For example, it's sent in this way. And moreover, the global basis corresponding to the simple object. So up to now, I'm talking about the bosonic extension. And now let me give you the example for fixing braid B. Well, let me give it the theorem first. Yes. What is K? I'm sorry. So, because of this, if you get this one, then the Grothendieck ring is the polynomial ring generated by the fundamentals. I mean, you consider the classes of those simple objects. UQ prime G is much more complicated, or it's much wild, because you need to consider the polynomial ring of infinitely many generators, but the cardinality is not countable. Let me see. I think I'm correct. That's the one of the reasons why we needed to consider Lagrange nuclear category. If you consider the whole UQ prime G modes and you consider Grothendieck ring, then it's too large to study. But in this case, it's a polynomial with countably many variables. Because you can take the parameter shift A here, and generically the parameter shifts are different from the original ones. So it produces a lot of new simple modules. So there are too many in some sense. So now let's fix the duality data. And let our BE is sigma I1 to sigma IR into positive braid. So my bold BI is this one. First, there exists a simple object C of K of I in G. Well, I think, yes, such that the image of the homomorphism of this is the, I think I erased something. This is the PBW generator. Then it gives the class of simple object CK. So what I mean is that under the homomorphism, the PBW generator is corresponding to some class of simple modules. The second, let me see. So let's consider the following category. So there are we need to choose D or GXD. So you don't need it. And let's consider the subcategory corresponding to I is the category generated by those simple objects. So I mean here I mean the monoidal subcategory stable by extension and subquotient. Then, yeah, that's okay. A subcategory doesn't depend on choice of I. On I. So to define this one, we need to choose I, right? But it turns out that it doesn't depend. So because it doesn't depend, we can write it as a, yeah, let me write it in this way. It only depends on the grade word B. So what I mean is that if you apply the grade relation here, then you will get the different expression for same B, right? Then you will get the different generators, but still the category are the same. And number 3, this is the, yeah, T 1 over plus minus 1 over 2 hat E is D will give the homomorphism between the Grothendieck and our Bosonic extension associated B. And it is an isomorphism when if we specialize the T equal 1, then it gives an isomorphism. Yeah, so number 3 is saying that we have a monoidal category which gives the structure of the Bosonic extensions. Right? So in this sense, we can say that this is a monoidal categorification. No, I'm sorry. So this category is a monoidal categorification of this algebra. Yeah, but until now, it's just saying that the tensor product corresponding to the product.
Next, could you explain the constraint of T equal to 1 on? Okay, can you explain what does it mean?
Yeah. So this is a it's a subalgebra of the Bosonic extension. So it's an algebra over Laurent polynomial ring. So you can specialize the T equal 1. Then you will get some algebra. That algebra is isomorphic to this one. Through this one.
The Bosonic extension, what does that mean in the sense of the extension of Bosonic? What does that mean?
So if you put T equal 1 here, then there is no error terms, so they are commuting.
So all kinds of the subcategories, okay, you have correspondent that is the T equal to 1 also considered in the case of the spatial unit equation.
So here, yeah, you should look at this one. So the Grothendieck ring of the subcategories we are interested in are all commutative ring, and this is a non-commutative ring.
Okay,
Yeah.
I got it.
Yeah, I think I spent too much time than I expect. So yeah, let me give you briefly the example. Really? I'm sorry. I'm sorry. Then yeah, then how can I do that? Yeah, 1 minute. Then yeah. Let me think about the moment. Yeah. So let me finish in 3 minutes. So example is B, if B is 1, 2, 1, 2. So sigma 1, sigma 2, sigma 1, sigma 2 is still here. Yeah. Then I calculate in the morning that the corresponding, the modules are, I think, yeah, I can write here. So this is C1, C2, and the C3, this is C3, this is C4. And we can calculate it. And I want to show you the following picture. So, because I didn't tell you about the cross algebras, I'm sorry. So I'll give you the picture. So here the nabla means the simple head of simple head of tensor product. So this is my notation, nabla. Then we'll get this diagram or figure in the category. So what does it mean? So those 4 simple modules are committing to each other. Their tensor product are simple. And this arrow has a meaning. So if you mutate, say the first variable here, then you will get the third generator. So I only replace C1 by C3, right? So this is the mutation. So this mutation relation comes from the following tensor product. This two, I think. So if you are familiar with the cross algebra theory, it means that the class of C3 is the denominator is C1 and I'm sorry, so C3 tensor. So I mean, so if we rewrite this one in the Grothendieck ring, then we'll have this one, right? And this is exactly the cross mutation rule for this keyboard. If you mutate this variable here, then you will get 2 monomials in the numerator, and the denominator is C1. That's the one here. So basically, we can do the mutations in the category. That's my point here. So what the important point is that this is a simple object in the category CD. Because in the Grothendieck ring or the cross algebras, you divide by some element by some simple object here. So you cannot guarantee that you will get some class of simple object here. But indeed, we have a class of simple object. And this mutation procedure is never end. I mean, you can, any kind of this seed admits a successive mutations for all directions. Yeah, I'm sorry, I think I spent too much time. Yeah, let me finish here.